Okay, now I'd like to talk about the discrete Fourier transform of square waves and sawtooth waves. So now that we've seen that we can end up with these harmonics in real audio, let's try to understand the harmonics a little better and make sure that everything's working out on some synthetic examples again. So I'll use the same DFT code I did before. Now I'm going to plot a square wave, and I'm going to plot its amplitude, its cosines, its sines, and its phase. Okay, so here is a square wave that goes through 2 periods over an interval of 1. So the equation for it would be, so as you can see, I write it as the sine function, which, you know, if anything that is positive will become a 1, anything that is negative will become a negative 1. This time I'm using the sinusoid, or the sine of 2 pi f t minus shift. Well, the shift is 0. So this is just a straight up sine. So you can see, you know, a sine wave starts at 0, goes up like this, then goes down, and then goes up, and like that. But you can see this kind of just rounds it up or rounds it down. So there's a square wave. If we look at the amplitudes, what we see is we go in this harmonic series, but skipping every other. So if I zoom in, what I can see here is, so this is a sine, this is a square wave that goes through 2 cycles over an interval. So if I zoom in on the frequencies here, what I can see is, okay, the bin at index 2 has something in it. Turns out to actually be 4 over pi. That's what some theory would predict. Then we skip a harmonic. So first harmonic of 2 would have been 4, but we skipped that one for the square wave. The next one we look at is at 6, which ends up being 1 over 3. So okay. So this is 4 over pi over 1. This would have been 4 over pi over 2. This one's over 3. We skip the one that's over 4. We go to the one that's over 5, and then we skip the one. Let me just zoom out a little more here. Okay, so yeah, so the pattern is, okay, a factor of 1 would have been a factor of a half. Factor of a third would have been a factor of a fourth. Factor of a fifth would have been a factor of a sixth, factor of a seventh, and so on. So let's see if we can reverse engineer this. This is actually called the inverse Fourier transform, which we'll talk a little bit more about next week. But I can try to reconstruct the signal by following what it says to do. So if I look, the phases are pi over 2 the whole way through. So cosine of pi over 2, that's actually sine. So what this means is, cosine of x minus pi over 2 is sine. So we're actually doing, remember, the negative sign. But another way of looking at it is they're all pure sinusoids. So I can say, all right, well, let me try to reconstruct this. So I had n equals 1,000 here. So I can say that one way I can write for k in range 10, I'll say y is equal to mt.0 is n. I'll say y plus equals mp.cosine of 2 pi. Here's a slick thing I can do. I can say 2k, 2 times k, plus 1. Let's see, will that do it? Yes, except I also have to say, okay, the first one is going to be 2 hertz. So I actually need an additional multiple here of 2 hertz. That would be the first one. So when k is 0, I get this is 0. So this times 1 is 2 hertz. When k is 1, this turns into 5. No, sorry, 3, which has been 6 there. 3 times 2 is 6. When k is 2, this is, then it's 5, and we get bin 10 there. Okay, 5 times 2 is 10. All right, so let's see what this looks like. Oh, and then I have to remember to divide it by 2k plus 1 as well. And I also have this factor of 4 over pi in the front, it turns out. So I'm being very precise with the square wave now because I'm actually matching it to what I see in the Fourier transform. So let's plot y and see what it looks like Did we actually get a square wave? No, we didn't. So what happened? Oh, because I need to multiply by t. It's all of that times t. Okay, and also, I made a mistake here because these are supposed to be sines, not cosines. Because I didn't have, none of the cosine components were actually anything, so they're all sines here. Okay, there we go. So this is an approximation of the thing I started with. Let me actually make the plot the same length. So this should be figure size 16:4. Okay, so let me just zoom out so you can see them all together. So what I'm saying is I actually looked at what the Fourier transform gave me. I noticed the pattern, that it was falling off as 1 over the frequency index, but only taking every other harmonic. And I was able to match what I saw there. If I use more of these harmonics, I should get a tighter square. And you can see now that the amplitude's correct. With this 4 over pi correction, we end up getting the amplitude of 1 here. Okay, so that's kind of a neat thing. What's even neater than this is what happens when you start to shift the square wave in time, what happens to the phases. So I made a little animation of this, which I'm going to show you now. So what I did was I shifted this thing slowly. I shifted this square wave slowly in time, and I plotted all the cosine, sines, amplitudes, and phases. So phase shift square 2.gif. Okay, let's look at this. Okay, so this is kind of crazy. Hang on, let me start over again. Okay, so as you watch this, you see that the amplitude doesn't change. So the amplitudes of the harmonics don't change. They're still in these same ratios. But the energy in each one shifts between cosines and sines. And what you see is that actually the phases for the higher frequencies change much more quickly than the phases from the lower frequencies. Because you remember, I'll keep this up here as I write the equation, but when, you know, our way of time shifting something was by saying, you know, each sinusoid got shifted as cosine or sine of 2 pi f t minus the shift, right? And I can expand this and write it as 2 pi f times t minus 2 pi f times the shift. This is the exact same trick used in the resay. So what we can say is, okay, let's see, we're getting back to close to starting again. We're almost there. But so what we can say is that frequencies that are higher have a higher phase change for the same shift. The same shift of f's leads to a higher phase change. Okay, watch, we're about to start off with all sines again. Here we are. We're all the sines. Okay, right at the beginning. And then, okay, you see that the higher frequencies, their phases change so much more quickly because it's the frequency times the shift. What the phase is, 2 pi frequency times the shift. And you just watch this beautiful pattern emerge as the square wave shifts over. Amplitudes are the same, but the phases are changing. So this is a really cool pattern. All right, now you can do a similar thing with sawtooth waves. Let's look at a sawtooth wave that goes through 2 cycles over an interval. So here it is. Now I see something a little different. So I have only sines involved, but they're actually all negative. So my phase is negative pi over 2, pretty much the whole way through. I also see that all the harmonics are involved this time. So I start off at frequency index 2, but I actually have frequency index 4 this time, and I have frequency index 6. So the sawtooth wave is different because all the harmonics are actually there. So I can start with code that was kind of similar to what I did before, but this time it's actually a little simpler because so what I find actually is this factor in front is 2 over pi now. And I can just say times k times t over k. And I guess I better start off at 1 so I don't get to divide by 0. Okay, so let's check this out and see what we get. So I'm just trying to match up what I see here. Actually, I'm starting off with the positive signs. They need to be negative. Okay. So I'm trying to match what I have here. So the first one I should have is oh, and I guess I better also do, it's really over, oh, no, this is okay. Okay, so yeah, the first one should be negative 2 over pi times sine of 2. So that, yeah, that should be frequency of 2. And then the next one should be 4, and that over 2. The next one should be 6, and that over 3. Okay, I think we got it. So let's plot this and see what we get. Okay, so this is looking a little bit like that. So we see we got the right shape here just by following what we saw in the Fourier transform, in the discrete Fourier transform. So just trying to match these up. And, you know, again, the more harmonics I use, the closer I get to that shape. Now, in general, for these sharp transitions, so for the square wave, you know, it was up and then it was down right away. Same thing with this Sawtooth wave. It's up and then it's down. For those sharp transitions, you need very high frequencies. And if this is an actually continuous function, you can define something similar to what we're doing here called the Fourier series. And it turns out you actually need infinite sines and cosines to describe sharp transitions. This is a discontinuity in the function, actually. It's a jump discontinuity. To represent jump discontinuities with sines and cosines, you actually need infinite frequencies. This was a problem for Joseph Fourier, who invented this stuff back in the 1700s. A lot of his contemporaries at the time were really skeptical because they're like, well, is this really the right way to represent signals? Because you have to go infinite. It just doesn't seem right. And they weren't even convinced that it actually matched in the limit. But it turns out it does. It does match in the limit. And Fourier was using it to solve heat equations. But actually, it ended up being at least as useful, even more useful, a century or two later in audio processing. So it's actually the perfect representation to really think about notes, because notes can be broken down into sines and cosines. So can the heat equation in some cases, but like the heat equation on a circle can be, if you have heat flowing around a ring or something, you can do similar things. But this is an even more, in my opinion, even more natural application than that. Okay. And I'd be remiss if I didn't show you a similar animation for the Sawtooth. So I have my square animation. I have one for the Sawtooth as well. And that's all gravy. So let's take a look. So same kind of thing. That the higher frequencies, their phases change more quickly as I shift this thing. And this looks just crazy. Okay, the last thing I want to point out is if I go back to one of these and I double the frequency, let's watch what happens. So here I go through 2 periods. Let's say I go through 4 periods. Let me actually, I'll just copy this code so we can look at them both. Yeah, that's fine. So that'll be the quickest way to do it. So yeah, let me make this frequency 4. And let's compare the two. So it's a little hard to see here, but actually what I can do is I can just, okay, whatever. I'll just delete that code and let's look at these two next to each other. So take a moment, pause this, and see what you notice. Like what happened after we doubled the frequency. So what you should see is that you get the same Fourier transform, but it gets scaled by a factor. So actually, when you compress a function, it actually expands the Fourier transform by the same amount. So this is one of these properties of the Fourier transform that's very interesting. When you compress a signal, its Fourier transform expands. And this should make sense because I'm saying, yeah, when I compress this thing, it goes through more periods in the same interval. That's the same thing as saying it has a higher frequency on that interval. In particular here, this one had a frequency that was twice as high as the other one. That means that all of the sines and cosines that are involved, their frequencies are going to get double. Okay, so that's just an interesting fact I want you to be aware of. Of course, this is very related to what we were seeing when we looked at our examples with the notes, because I saw that for an E3, they look like this. The spacing between them was 330 hertz, but when I went to an E4, which was double the frequency, I saw that the spacing between them was 660. So it's the same thing. I just want you to be aware of that. It's just an interesting thing that happens. Kind of the opposite thing happens in the frequency domain to what happens in the time domain. So you compress, you expand. In the time domain, if you expand, you do the opposite. I make this only go through one period. Then I would actually compress the frequency. So let me do that on this one real quick. So if I make this only go through one period of a sawtooth, then everything got compressed. Okay, this goes through 4 periods, so actually this got expanded. All right, very good. So I just wanted you to understand that stuff, and I'll just ask a quick comprehension question on that on Canvas, and that's it for this module.